Another phenomenon that we would like to describe with mathematics and also graphs are oscillations. Oscillations are common events. You see it in things like bungee jumpers jumping off a bridge, where a person ties bungee cords to their ankles, the other end to the bridge, and they jump off and they go up and down, bouncing back and forth. Anytime there is something that does a repetitive motion from going from point A to point B and back and forth, that's what we describe. That's what an oscillation is. There can be things like a car in a ditch is even an oscillation. Say you try to push your car out of a ditch, you roll it up toward the edge of the ditch, but you don't quite get it out, so the car rolls back down and rocks back and forth in the ditch. That would be an oscillation. Or a grandfather clock, looking at the pendulum, you see it swing back and forth. Another example of an oscillation. There are many such things in the world, and I'm sure you can think of a few more. But let's go on and talk about how do we make a mathematical description of an oscillation. Well, we start out by thinking about what is unique about oscillating objects. Let's take an example of a spring. We have a spring attached to a wall, and so one side of the spring is attached to the wall, the other side of the spring is attached to a mass. Now there's a unique position for any oscillator, and it's easier to describe in terms of the spring. When the spring is relaxed and not exerting any force on the mass, we call that the equilibrium position. So that means that the spring isn't compressed or stretched, so at the moment shown, the mass is just sitting still at the equilibrium position, which we mark with a dashed line. We're going to assume that the floor shown is slippery, so we don't have to worry about any sort of friction or any loss of energy in this problem. Well, if we leave it there, nothing will happen because there's no forces acting on the problem and it becomes rather boring. So if we move the object away from this position and release it, it'll oscillate about the equilibrium position. So let's do that. If we move it over a distance a from the equilibrium position to a point we're going to call the release position, then if we let it go, it's going to be pulled back toward the equilibrium position by the spring. It'll pass through the equilibrium position because it'll be moving at a high velocity at this point, and then it'll start compressing the spring, and because no energy is being lost due to friction or any other force or any other non-conservative force, we find that the mass will slow down, come to a stop at a position of minus a, or a distance a to the left of the dashed line, and then it'll start to accelerate again back to the right, and it'll just do a repetitive oscillation about the equilibrium position. So it's good to use these unique positions as your origin. So let's take the equilibrium position as the origin. We're going to use the equilibrium position as the origin, and we also have to pick time 0. So we're going to take time 0 as being the release time. So you move it over to a distance a, and then when you release it, we're going to call that time 0. This is a unique time because after this, the only forces acting on the problem are the spring, or due to the spring. In that case, we have an oscillation that goes from a on the right to minus a on the left, or we can write this down in terms of an x position, and x is a function of time, is equal to a, that's the displacement that we made originally from the equilibrium position, times a cosine. The cosine is an oscillatory function, and the argument of the cosine here is 2 pi times a frequency, which tells you something about how fast the oscillation occurs, times the time. Note that when t is equal to 0, cosine of 0 is 1, so we get the release position, a away from the equilibrium. If we wait a time t so that f times t is equal to half, then we have cosine of pi, and that's equal to minus 1, so we end up with the position of the mass when it's at the closest approach to the wall on the other side of the dashed line. So we're at minus a then. Okay, let's go ahead and plot them. So we're using this, remember this is the equilibrium position at the origin. Here's our function, x of t is equal to a times cosine 2 pi f times t, and we see this cosine sinusoidal function. At time 0 it starts at a, it goes through the equilibrium position at 0, goes on down to minus A, turns around and then goes back up to the original release position at A, and repeats this over and over. How would this change if we used a different point of origin? Another interesting point is the point of release. It's unique and then equally good as equilibrium position, so we could use that point of origin also. Well, at time equals 0, if we use the origin as the point of release, that means that x at time equals 0 has to be 0. So when you release it, is time equals 0, and the point of release is also the origin, so obviously at that point x has to be 0. Well, to get from the equilibrium position to this new position, we had to displace it by A. So if we want to describe the original equilibrium position, well, that's minus A now. So if we want to write down the new equation, we just take our A times cosine 2 pi f of t that we found for the case when the equilibrium position was the origin, and subtract off the new value of the equilibrium position, so minus A. You can see this will work, and so now the plot goes from a position of 0 when at the release down to minus 2A when we're closest to the wall, and repeats over and over. Okay, I think we've talked enough about the origin. So the frequency is a measure of how fast the oscillation occurs. If we look at this graph, we see that it starts at A, goes down to minus A, and back to A in a time of ½ a second. Or, as we continue on, we see there's a second cycle that occurs from ½ a second to 1 second. So there are 2 cycles in 1 second. That's exactly what we mean by frequency. A frequency of 2 Hertz is 2 cycles per second. A slower oscillation is shown in the next graph. Here we see that you start at A and go to minus A and back to A in 1 second. So this is a graph of a 1 Hertz with 1 Hertz frequency, or 1 cycle per second. We've talked about 3 different characteristics of oscillations. We've talked about amplitude, how much we've displaced our object from the equilibrium position. We talked about the equilibrium position, which is the unique position where there is no force on the object. And lastly, we've talked about frequency. So now we have a pretty good description of what an oscillation means and how to describe it mathematically and make graphs. So it's your turn.